This is the 2022 AMC 10B, problem number 19. Each square in a 5x5 grid is either filled or empty and has up to 8 adjacent neighboring squares, where neighboring squares share either a side or a corner. The grid is transformed by the following rules. Any filled square with 2 or 3 filled neighbors remains filled. Any empty square with exactly 3 filled neighbors becomes a filled square. All other squares remain empty or become empty. A sample transformation is shown in the figure below. So we can go case by case through every single cell in the grid here, right? So we can write down the number of neighbors it has that are currently filled, like 1, 1, 1, 0, 0. It's not that hard to fill these numbers in. 1, 1, 1. This one's touching 2. This one's touching 3. This one's touching 3. This one's touching only 2. Oh, no, that one's not touching 3. My bad. That one's touching 4. This one's touching 2. This one's touching 1. 1, 1, 2, 3, 2, 1. This one's touching 1. Yep. Yeah, and that's everything. So now we follow the rules in the figure, which is basically that we go, okay, also the filled squares, we have to keep those in mind. This one has 1 neighbor, this one has 2 neighbors, and this one has 1 neighbor. Okay, any filled square with 2 or 3 filled neighbors remains filled. Well, as you can see here, there's 3 of these cells that are marked with 1, so they're supposed to become empty in the next term. And as we can see, these 3 are like they become empty, and this one remains filled because it has 2, which is either 2 or 3. That meets the conditions. And for the rest of the numbers, right, only the ones that are have exactly 3 neighbors are the ones that become filled, which are this one and this one, which is why in this figure we have this one and this one. So that explains basically what this is showing. Okay. Now, what is the problem asking? Suppose 5x5 grid has a border of empty squares surrounding a 3x3 subgrid. How many initial configurations will lead to a transformed grid consisting of a single filled square in the center after a single transformation? Rotations and reflections of the same configuration are considered different. Okay, so this is a very strange combinatorics problem, but this is actually based around like a certain mathematics like thing that was invented. This is like, if you've ever heard of it, this is like Conway's Game of Life right here. This is what this is. So it's asking us basically how many different ways are there for us to determine a 3x3 patch of squares such that after one step we have 1 square left in the middle. So basically what we want to do is we want to divide this into cases that are countable, right? There are not even that many scenarios to go through. And we know that by looking at the answer choices, right? Less than 30, that shouldn't be too many to count. So it's just a matter of splitting up the cases in a way that makes it bearable to count. So let's divide it into 2 different cases. Either this square is empty and it becomes filled, or this square is already filled and it stays filled, right? So we can go with that. Let's first start with the case where this square is empty, right? All right, so let's draw our 3x3. And basically, the key thing about it going from being empty to being full is that it needs to have exactly 3 neighbors. So what does this mean? Well, that means that this square is empty, and exactly 3 of the squares here have to be full, right? And because if there's exactly 3 in that range that are full, it's going to make the middle square full. And if not, then it's going to fail. So that's the only way. However, it's much, you can't just be like, oh, it's 8 choose 3, which is equal to 56, because, well, that's a lot bigger than all of the other choices we have. And the reason for that is because almost all of them don't actually work. So let me try to explain this. For example, let's just pick 3 arbitrary squares. All right, what's the problem with filling in these 3 squares? Well, the problem with that is this square right here. You see, this square is touching exactly, oh, it's not, my bad. But for example, this. So for example, here, this square would be touching exactly 3, right? And that would cause it to light up along with this one, right? And that's one of the ways, right? By accidentally creating another 3 neighbors square, right? So basically the next step would have both of these filled instead of just the center one. And the other way for it to fail is basically for too many of them to be touching. Like what I mean is, like, for example, if any of them touch, it instantly creates a contradiction because this one has 2 neighbors for well, it doesn't, but for example, let's say we put them like this, then this one would have 2 neighbors, 2 neighbors, 2 neighbors, and they'd all stay lit up, right? So basically we need to be careful to make sure that they don't all touch at one spot, and also to make sure that we don't have, because yeah, if they're ever chained together like this, it's going to fail because of the middle one has 2 neighbors. So on the next turn, right, these 2 are going to get erased because they only have 1 neighbor, but this one's going to become filled, and then we'll have both of these filled, which is not what we want. So yeah, just to reiterate that. And actually, the astute observer might notice that, for example, because we're working in a 5x5, right? These squares, for example, could also contribute to it, specifically if these 3 are all lined up here, right? Then it would lead to this one being filled and this one being filled, which would contradict it. But this case is already taken care of by the second thing we said, because these form a chain. So this one has 2 neighbors, so it's going to stay filled. So we don't actually need to worry about that. But it's good to keep in mind. It doesn't affect this problem at all, but it's good to keep that in mind. So basically, the question is, how many different ways are there to position the lines in the way we want to, right? Okay. Well, we should just look through all the different patterns we can get, because we want to be careful about this. We just want to look through all the different patterns we can get and go through if each of them work or not, right? So basically, I'll say, like, I'll just pick like different patterns of 3 of them in an arrangement, and then I'll calculate the number of ways to like rotate and reflect them. So for example, this is one configuration, right? This configuration, in this case, this configuration would work, right? So that would add on to our counter, right? But for example, this configuration wouldn't, right? So let's just go through all of them. And in the end, we should have a total of 56. That's how we can check it. And basically, these are all the ones that I'll write down all the possibilities that work here, and I'll write all the ones that don't work here, right? So the first scenario is where they're touching in a chain, right? So they can touch like this, all 3 in a line. There's exactly 4 ways for that to happen. And of course, this doesn't work because of what we've already said about them forming a chain. The middle one has 2 neighbors. Another way to do this is for it to be like this, right? This is also another chain. And this one, if we take reflections and rotations into account, this has a total of 8 different ways of orienting it in any different way. So we'll put that down there as well. And another way to chain 3 of them together is to put it like this, right? This is still counts as a chain because this middle one is still touching 2. The number of ways to do that is 4. And the final way to chain them together is to connect them like this in this L shape, right? And the number of ways to do that is just 4. Okay, so we've gotten rid of all the chain ones. So now none of them form a chain, right? So now we'll just go over ones that have like a block here, right? So if there's a block here, like a 2x1 block, we could have the point over here, which we know doesn't work. And in total, there is 8 different possibilities for this. We also have the condition where the point is over here. And once again, for the same reason, right? These 2 squares will both become alive next turn. It'll also not work. And once again, there are exactly 8 configurations here. And we can see that most of them don't work, which shows us why the total sum here is not going to be even close to 56. That's why, because most of them don't work. We could also have the point over here, and this one would actually work, if I'm not mistaken. Yeah, no, this would work. Because all of these cells will die, and the only square that's connected by all three of them is that square. So this is the first example of one that does work, and it has 8 cases. Okay, well, and then the other squares will cause a chain. Okay, so it's just these 3. Okay, so we've gone through every single 2x1 case. So let's just do a quick recap through the cases we've gone over, like just sum these up and make sure, like, let's see how far we've gone. 32 plus 12 gives us 44. Okay, so there's 12 cases left. So what are these cases? Well, these are the cases where, well, first let's go over this case where 2 of them are connected like this, but they're connected diagonally. Once again, we can't form a chain, which leaves only this shape. So it's like a Y shape, right? It's like a little Y shape. So does this work? The answer, yes, it does work, because these will all die, and this is the only cell connected by all 3 of them, and the number of ways to orient that is 4. Okay, so now we have eight positions to go, and now we're supposed to position them so that none of them are touching, and there's actually only 2 ways to do this, and that's to position them like this. This works, right? And the number of ways to position it is 4. And finally, we have this position, and this is the final position, and there's 4 ways to do that as well, and it does work as well for the same reasons we've already talked about. So basically, by counting, we've determined that the number of cases that actually work here are 20 for this case and 36 for this case if we added that up. Okay, so that is if, first of all, that eliminates A and B, and also now we only have 1 case left, and that's basically the case where this square is filled in to begin with. So this case, actually, it might seem like it is more work, but it's actually much less work. Like, you might think it's more work because, oh, it can be surrounded by either 2 cells or 3 cells, but it's actually a lot less work because, as we'll see, it is very easy to accidentally cause another cell to be lit up, right? So basically, for example, let's say that there's just a cell lit up in the corner. Well, we know that these 2 cells can't be lit up, because if they were, then what would happen is, for example, let's say that this cell was lit up. Well, then no matter if this cell was lit up or not, this cell would have either 2 or 3 neighbors, so it would definitely stay alive to the next stage. So that would cause a contradiction. So basically, if we have a corner, like a corner filled in, that means neither of these can be filled in, which is already like eliminating a lot of cases. So we can further break down these cases into either like what I'll call full 2 and I'll call full 3, right? Because these correspond, well, these are both full because this element in the middle is full to begin with. And I call them 2 and 3 because this one is the case where we have 2 of the 8 surrounding it to be filled, and this be the case where 3 of them surrounding it to be filled. Okay, so let's first look at full 2, right? So how many different ways are there to position the 2 lit up elements, right? So as we've already talked about, they can't be touching at all. And actually, it goes even further than that, because let's say that this cell is lit up, right? Then actually, in addition to not being able to fill in these squares for the same reasons we talked about before, we can't actually fill in these squares as well. So that really eliminates a lot of the possibilities. So basically, the reason for this is, let's say that a square is a consecutive to it is filled in like this. Well, then basically, for the same reason as we've already talked about, we can't have this square filled, because if it did, then this square would have exactly 2 neighbors and it would stay lit to the next stage. So therefore, this cannot be filled. But then look at this square, it has exactly 3 neighbors. Guess what's going to happen? It's going to become filled. So that's a contradiction. So neither of these can be filled in as long as we have at least 1 on a corner. So if we have 1 on a corner, that already really eliminates a lot of scenarios. And actually, it goes even further than that, because actually neither of these 2 can be filled in either. Because if this square were filled in, this would have exactly 3 neighbors. If this square were filled in, this would have exactly 3 neighbors. So actually, filling in a single corner results in only 1 other square being left. And this is our only case here. And that leads to only 2 cases. And as you might be able to guess from this, that means that full 3 is actually not, like, there are no solutions that exist. This cannot exist. This is actually just 0. And the reason for that is, if we have 1 in a corner, none of these can be filled, and we can only fill in at maximum 2, which contradicts with the fact that we're trying to fill in 3. And otherwise, we have to fill in 3 edges. And this is the only configuration that works, considering like reflections and rotations, whatever, right? And that would, this doesn't work for a number of reasons. This one has two neighbors, so it's going to stay alive. This has three neighbors, so it's going to stay alive. This has two neighbors, so it's going to stay alive. This is three neighbors, so it's going to come to life. Three neighbors, three neighbors. So we're actually just going to get this huge block of cells. That's not going to work for a number of reasons. So this actually has no solutions. And that just gives us 22 and 0. And there are much fewer solutions than you might have expected. 20 plus 2 plus 0 is just 22. And that's choice C.